Hello, today I'm going to demonstrate how to obtain the formula for alpha particle scattering experiment. If you want to know the experiment itself, then you have to watch another mini lesson. Here we just use an atomic model which contains a tiny positively charged center called the nucleus and the electron around it. Because electron mass is so small compared with proton and neutrons, so here we don't have to consider the contribution from electron during the scattering experiment. So here is a diagram about this experiment. This particle will represent nucleus of helium. Here is nucleus of gold. So it is reasonable to assume that during the entire scattering, the position of the gold remain unchanged. So here is a coordinate I have drawn, where this is our x-axis, these are y-axis. So this is the initial position of nucleus of alpha particle. This is the position of alpha particle after scattering. Now, here we have to introduce a very important variables called scattering angle. So this is a theta. So the first variable is theta. The second important parameter we're going to discuss is the distance. The initial distance of alpha particle from the center line where the nucleus of the gold located. So that's called B. The objective of this formula is to define the dependence of scattering angle on the parameter B. So this is the function to be obtained. Obviously, if the B changed, the angle will change. If the B is very large, and you can imagine that the scattering angle will be very small. On the other hand, if the B is very small and the scattering angle will increase. In the extreme case, if B equal to 0, we will end up with what we call head-to-head collision. Obviously, because of repulsion, the initial velocity of alpha particle will decrease until it actually reach to 0. So, in the meantime, the distance between the two nuclei reach to the minimum and eventually return and rebound. So that is why in alpha scattering experiment, Rutherford first observed some particles are actually reflected by the heavy nucleus of gold. So in this case, the scattering angle will be pi. Now how do we start? First, we need to find the force. So this is arbitrary position of alpha particle during the scattering. Distance between the two charged particles will be called r. According to Coulomb's law, the force in this case must be repulsive. The force acting on alpha particle will be centrifugal. So that would be the Coulomb force acting on the particle. How about the other condition? We can assume that initially the alpha particle is moving along the horizontal position. And after that, after collision, the initial velocity will change direction. So that is the velocity of alpha particle after collision. So the initial velocity can be called Vi, it's Vi, and this is called V finals, V finals. Next, let's consider if any conservation law can be used to solve this problem. First, let's consider the energy conservation law. Since the Coulomb force between the two particles is what we call conservative force, so the total energy must be conserved. The total energy will equal to kinetic energy plus potential energy. In this case, the kinetic energy can be written as half mv squared, and the potential energy of the electron, while the electron potential energy can be written as k times q, capital Q, and divided by r, where q is the charge of alpha q, so with capital Q to represent the charge of nucleus of gold. So because the energy is conserved in this case, because the total energy is conserved in this case, we can argue that the change in kinetic energy will equal to 0. Bear in mind that the limit, the potential energy when r approaches to infinity will equal to 0. So this condition will give us that the initial velocity will equal to the final velocity. Can we simply use v to represent the magnitude of the initial and final velocities? That also gives us that the magnitude of the momentum will remain the same. So momentum is a vector, so we can argue that initial momentum will equal to final momentum, which can be simply written as m times v. If we return to the diagram, so this arrow can also represent the initial momentum of the alpha particle. This can also represent the final momentum of alpha particle. Okay, that will equal to m times v. Oh, notice that the direction of final momentum and horizontal line will give the same theta, that is a scattering angle. Here is opportunity to introduce a theta in relation to change of momentum. So that side will represent the change of momentum in y direction in this triangle. So from this triangle, we can obtain this simple relation, that is, and the delta p y component over p will equal to sine theta. Okay. Therefore, we can argue that delta py will equal to p times sine theta, or equal to mv times sine theta. This is our equation 1. Equation 1 is obtained based on energy conservation law. Second, let's consider another basic law in physics. According to impulse momentum theory, the change in the momentum can be written as impulse. We can simply write the change in the momentum along y direction can be written as f y components times dt, and the integration from the beginning to the end of the scattering. Okay, so this is our second equation. So this is the second equation that is come from the impulse momentum theory. Now, how to write the y components? We have to return to the diagram. So this is a force. This normally the force can be written as a vector form. So if we want to find the y components of this force, so we have to draw the diagram here. So this will be our y component. So this side will be Fy. If we introduce angle here, can we call beta? Y component of the force will equal to the force. The magnitude will equal to the magnitude of the force times cosine beta. So this is another angle different from the theta, with theta is a scattering angle. But these two angles are related. So if we just consider if the angle, in this case, in this particular case, theta will represent, here will be represented theta in this case. The position in this polar coordinate, theta is this angle, right? So this angle. So if you consider this triangle here, if we consider this triangle here, this is a right angle triangle here, we can argue that in this triangle, beta, so we just write down here, in this triangle, we can argue that beta plus pi minus theta will equal to 90 degrees. So this is a right angle triangle. We'll write down these two important formula down here. Fy components, so the force, the y components of the force can be written as F times cosine beta. Okay. And here, what is beta? So beta, where beta plus pi minus theta will equal to 90 degrees or half pi, which will give that, so if you just do some simple algebra, so beta will equal to, in this case, will equal to, so beta will equal to theta minus pi. That will lead to that cosine beta will simply equal to sine theta. Okay, so what we have is Fy will equal to the F times sine theta. This secondary angle, the theta, the secondary angle show up again. So these are equation 3. Thirdly, we have to use another basic law in physics. What is F? F is determined by Coulomb's law, electrostatic force between the two positive charges in this case. Coulomb's law says F will equal to the magnitude of the interaction will equal to K times the product of two charges divided by R squared, where R is the distance. So if you look back here, so this is the R is distance between the two charges. So this force were determined by Coulomb's law. So this can be called equation 4. So if we substitute equation 4 into equation 3, we have Fy equal to KQ, capital Q, divided by R squared times sine theta. Okay. So now we obtain the formula for the y components in equation 2. So therefore, according to impulse momentum theory, the change in the y component can be simply written as integral. Origin is Fy dt from 0 to infinity. Can we put a constant outside integral? Is K, that's a constant in Coulomb's law, capital Q, and what we have remain is sine theta, and divided by R squared and time delta t from 0 to infinity. Notice that inside the integral of the equation 6, there involve 3 variables. Both the angle and the distance from the nucleus of gold is time-dependent variable. So perhaps some people will give up at this moment, including Rutherford, because he's not very good at mathematics. To solve this problem, we have considered another basic law in physics, that is conservation of angular momentum. So that is angular momentum conservation law. So what is the angular momentum? So by definition, an angular momentum will equal to the vector product of the position vector and the linear momentum. So let's consider how to write the momentum in this case. First, we just consider if there's no positive charge here, the alpha particle will move along this horizontal line. When the alpha particle arrived here, it will be easier for us to determine the initial angular momentum because this b remains a constant. So at this particular moment, in the absence of positive charge, the distance between the alpha particle and the origin is simply b, and the linear momentum is can be simply written as m times v. So in this way, initial angular momentum can be written as b times mv. How about the momentum at angle theta and distance from the origin is r? That can be written as r times m r and times the theta, the first derivative of theta. Here we have used a formula that the linear velocity can be written in the polar form, so that would be the polar form of initial velocity, where the theta prime is actually represent d theta dt. Can you see theta appear again in this formula for angular momentum? Because the force is a central force, therefore the angular momentum is always conserved. So in other words, at any moment, the change of the angular momentum is always zero. So that is a conservation law of the angular momentum. Because of that, we can argue that these two momentum, so initial momentum, were equal to the momentum at any position. So we can argue that so mbv were equal to m r squared d theta dt. Okay. Now, if we compare with these equations, this is our equation 7. If you compare with equation with 6, there is a possibility to substitute dt by d theta. Let's do that. M is cancelled. We got dt were equal to r squared d theta divided by b and v. If you just remove the theta on the other side, this is dt divided by r squared, will simply equal to d theta over b times v. This is our equation 8. Can you see that? So can you see we have the dt over r squared in equation 6. So if we substitute equation 8 into equation 6, delta py will equal to kq capital Q, and we got the sine theta here and d theta. Anything else? We have divided it by b and v. Because we have used theta to replace time, therefore the two limit of integration has to be adjusted. At the beginning, time 0, the angle is pi, so it's in negative infinity. After condition, eventually we reach this particular angle, that is the angle associated with the b. So this will be our equation 9. The integral from pi to theta sine theta d theta will simply equal to negative cosine theta, and from pi to theta. So that will give us so the cosine theta minus negative 1, and that will give us 1 minus cosine theta. Okay, we can use some formula in trigonometry function to sine square half theta or equal to 1 minus cosine theta. So the integral can be rewritten as, we times 2 here, we got a sine square half theta, half angle. These are equation 10. So we substitute the integral here, we're equal to 2k, refer 2k q, capital Q, divided by b and initial velocity v, sine and time, all of them times sine square half angle. So this is our equation 11. Nearly finished. Can we recall? We just recall delta py can also written as mv times sine theta. So mv times sine theta. Okay. If you use a sum formula for the sine theta, we can rewrite this equation as 2mv times sine half theta times cosine half theta. So that is our equation 12. Here we got two formulas for change in the momentum along y direction. So they must be equal. So finally, combining equation 11 and equation 12, we have 2mv times sine half theta times cosine half theta must be equal to this side, which is 2k q, capital Q, divided b times v and sine square half theta. To rearrange that as the formula here, we will have the tan half theta will equal to, if you put everything on the other side, so that became the mv square divided by k q, capital Q, and times the b. So also recall the head-to-head condition. So when b equal to 0, okay, so what we have is that the initial kinetic energy will convert it to totally convert to the potential energy. Okay, so that is half mv square will equal to the minimum distance between the two nuclei times the k times the q and the capital Q. So here we can simplify the expression. So therefore mv square divided by kq capital Q, right, that will simply equal to 1 over d. That will equal to 2 over d. So this is our equation 14. So if we substitute, if you substitute equation 14 into equation 13, we have tan half theta equal 2b divided by d. D is the minimum distance for head-to-head condition. Okay, so that would be give the theta or equal to 2 times the inverse function, tangent function, and 2b divided by d. So that is number 15. Unfortunately, there is a subtle mistake that lead to the incorrect conclusion. This is conclusion of what we have obtained, where d is the minimum distance during the head-to-head condition. But the correct formula is, so this is incorrect and this is correct. So what's wrong? This is a scattering angle. We put b here because theta is dependent on the parameter b. Now we have integration to be made, the integral sine theta and sine theta d theta. The limit we use is actually going this side. This means that it's from pi to theta b, right? And that will give us negative cosine theta. It's from pi to theta b, and that will give us 1 minus cosine theta b, because the sine square half theta will equal to 1 minus cosine theta b and divided by 2. Therefore, the integral we have can be written as 2 sine square theta divided by 2. This is b. But this is incorrect. We have to take into account our direction of the theta. If we use the theta from this side, the initial position should be theta b, and the final position should be pi. Okay, so this is a subtle difference. So let's look what happened here. So that will equal to negative cosine theta, get theta b pi, right? So that will give us negative pi is negative 1, okay, minus theta, so the minus cosine theta b. Can you see the subtle difference? The result will be 1 plus cosine theta b. So according to another trigonometry formula, cosine square half angle formula equal to 1 plus cosine theta divided by 2. Therefore, the correct integral must be written as 2 cosine square theta b divided by 2. So this is the correct formula for integral. Now if we substitute this result into our final, we got to say, remember, you just recall the delta py is equal to p times sine theta b. Okay, and then we just rewrite it as mv times 2 sine theta b half times cosine theta b half. Okay, if you compare two sides, we just write the sine theta b divided by cosine theta b divided by 2. On the other side, we got a cosine, so instead of sine, so we got, so there are other coefficient. There are other coefficient here, but here would be, here is a cosine square theta b 2. Okay, so in this case, if we remove this side, if divided by this on both sides, on both sides. What we have is simply that this coefficient here, that will become cosine theta b half divided by sine theta b half. That will give you cotangent theta b and divided by 2. Finally, we should get the correct one as cotan half theta b will equal to b divided by d. So this is correct formula.